35 summation as n goes from 0 to infinity, sine squared n over n squared plus 1. This one, at least to me, is not really familiar right away as to which technique to use. So let's go down our list. This is what I'm going to be thinking through as I see a random problem. Can we use the test for divergence? If we take the limit as n goes to infinity, the bottom's going to blow up, right? So it's going to make it go to 0. Sine squared n, well, this as n goes to infinity, it's going to oscillate between -1 and 1. So this intuitively should approach 0 as n goes to infinity because this is fixed between -1 and 1, the top, but the bottom keeps getting bigger. So it's going to, even though this is changing between -1 and 1, this will make it approach 0. So it seems like it will work out. So, I mean, it will go to 0. So the test of divergence does not work out for us. Okay. Can we do the integral test? This does not look like a fun integral to evaluate. Fun meaning easy. So let's try to avoid that if possible. And actually, remember I was saying, actually, this is always positive, so never mind. So going back to the test for divergence, this is going to be oscillating between 0 and 1. Okay. But going back now to the integral test, this might not be positive and decreasing. Okay. So we might not be able to do that, but as I said, this if it were positive and decreasing, mainly the decreasing part I'm questioning, this one probably won't be easy to integrate. So let's skip that. Test for alternating series test. Sorry. Can we do that? No, this is not alternating series. It's always positive. Okay. Can we do the ratio test? I don't want to evaluate sine squared of n plus 1 divided by sine squared n. That seems complicated, so let's try to avoid that if possible. Root test, the whole thing's not to n power, so probably not that. Maybe one of the comparison tests. Now, of course, the question is, what do we compare it with? And do we do the direct comparison test, or can we do the limit comparison test? So I chose to do the direct comparison test because we know that. So let's go through this now. Sine squared n is less than or equal to 1, as I was kind of saying earlier. Sine is between -1 and 1. So sine squared is, if we square it, it's less than or equal to 1 all the time, okay? So we can compare it with 1 over n squared plus 1. Since this guy is less than this guy, this is oscillating between 0 and 1, the sine squared. This is a fixed constant 1. So this guy up here is going to be smaller, okay? And now we can do another comparison. Since this guy is less than this guy over here, we're dividing by more, so it's going to be less. The final value is going to be less, okay? We know this is a convergent P series, P equals 2, yeah? So since this converges, this guy's even smaller, this guy's going to converge as well. And since by that argument, this converges, this guy's even smaller, then this guy's going to converge as well. Okay, so this is what's the word I'm looking for? Not a direct comparison test in that I'm directly comparing this and this, even though I probably could have, but for the sake of my explanation, I'm showing that this guy's smaller than this one, which is smaller than this one. This guy's convergent, right? So things smaller than it, which includes both of these, including our original one, is going to converge as well. That's the spirit of the direct comparison test.